Hi, welcome back. In this session, I am going to talk about multiple regression model diagnostics. So, what we are going to do in this session is how a model is validated or diagnosed before we start using the model. So, these are some of the steps we go through to validate the model or diagnose the model. So, the first thing is to test for the overall model fitness. So, we use measures such as R square and adjusted R square for testing the fitness of the model. The next is test for overall model statistical significance, which is achieved through F test, and we can also go and test for portions of the model. So, basically suppose let us say I have 10 variables and there are 2 new variables come in, I can check whether those 2 new variables adding value to the model. So, that is done through what we call as partial F test, and partial F test plays a major role in stepwise regression model building. We are going to discuss that later, and we have to also go and check for the individual explanatory variable and their statistical significance, so which is achieved through t test, and we have to go and test for normality, homoscedasticity, and also check for multicollinearity and autocorrelation. So, after we go through all these tests, only then we can actually accept the model and try to use the model for a given context. So, first let us try to understand the coefficient of multiple determination. I am using the term multiple determination because this is a multiple linear regression. It is basically a coefficient of determination. So, the equation for R square or coefficient of multiple determination is SSR over SST or 1 minus SSE over SST. So, higher the value, it is better. In this case, I am giving an SPSS output where I have looked at the DAD case again. My y is the treatment cost and x1 is the body weight and x2 is the HR pulse. So, here the R square is 0.173, which basically means 17.3% of the variation in the treatment cost is explained by the model, which is body weight and HR pulse. It is interesting to note that the R square will increase when we add more variable. So, typically what happens is, if you look at R square, which is SSR over SST, the numerator SSR will keep on increasing as the number of explanatory variable increases, or if I use the expression 1 minus SSC over SST, the SSC portion will keep on decrease when I add a new variable. So, basically whenever we add a variable, the R square will increase irrespective of whether the variable that we added is statistically significant or not. So, let us look at this example. See, here I have included body weight and HR pulse, and the last variable SL is the serial number. So, it is basically the case number in that data set. Remember, in case of die another day example, I had 248 observations. So, this SL is basically 1 to up to 248, and it has increased the R square to 0.33. Remember, when I had the first 2 variables body weight and HR pulse, the R square was 0.173, but the moment I brought in SL, the R square almost doubled, it went to 0.33. So, here what I am trying to convey is that you may come up with a variable which may not have any statistical significance, even then you will see that the R square increases.
Prof, why does the R square value increases when we add more variables?
Why R square increases? Remember the logic that we use to estimate the regression parameters. So, we have SSC equation, sum of square equation. All we are trying to do is minimize that sum of square errors by finding optimal values of beta naught, beta 1, beta 2 and so on. So, when you add a variable, it has that much flexibility to minimize the error. So, that is why we see that the R square value increases whenever we add a new variable. Once I have this problem, I have to be careful in using R square. So, what we do is we actually have another measure which is called adjusted R square. In case of adjusted R square, what we do is we normalize both numerator and denominator with respect to the degrees of freedom. So, adjusted R square is nothing but 1 minus SSC over n minus k minus 1. Remember, SSC has n minus k minus 1 degrees of freedom and SST has n minus 1 degrees of freedom, where we lose 1 degree of freedom because we are estimating the population mean from the sample itself. So, the adjusted R square is an improvement over R square to deal with an issue that the R square will keep on increasing whenever we add a variable. So, here in this table we see that when I have the equation y equal to beta naught plus beta 1 body weight plus beta 2 HR pulse, our R square is 0.173, whereas our adjusted R square is 0.167.
Sir, how do we use adjusted R square?
Now, the way in which we use adjusted R square is basically to ensure that whatever variable we add is adding value. So, typically what can happen is, whenever we add a new variable, the R square may increase, but the adjusted R square may not increase. So, that is an indication that the added variable is not adding value in explaining the variation in y. So, look for whether adjusted R square is increasing rather than R square is increasing.